All right, let's get started. We're talking about paracyclic reactions still, and I keep telling you over and over again that there's 4 types of paracyclic reactions. These are the canonical types, and if you can keep these 4 canonical types, right, there's other ring sizes, but if you just focus on the 6-membered rings, it's easy to keep them straight. So we spent quite a bit of time talking about Diels-Alder reactions and other cycloaddition reactions, dipolar cycloadditions, things like that. And then we talked about this variant where you replace one of the pi bonds with a sigma bond, and that's called an ene reaction. And so now we're going to spend one lecture talking about electrocyclic reactions. And instead of having 2 components coming together in these next 2 classes of paracyclic reactions, it's intramolecular. So let's go ahead and talk about electrocyclic reactions. So one issue that you need to address with electrocyclic reactions is what's favored. Are you going to close a ring or are you going to open a ring? And all we have to do is reverse the arrows and you can explain either way. So if I take these electrons and attack here, I can make a ring. And if I do it the other way, I can break the ring. Just by reversing the arrows that I push. So how do you decide what's favored or what's not favored? Here it's kind of easy to decide. Really what we're doing is we're trading. I've got 3 pi bonds, 3 carbon-carbon pi bonds in my starting material. And in my product, I've only got 2 carbon-carbon pi bonds. I've traded a weak carbon-carbon pi bond for a strong carbon-carbon sigma bond. Dean, do you have a red pen that you can give me for to draw, or anything colored? Okay, so I mean so of course it's going to be favored to trade a weak carbon-carbon pi bond for a carbon-carbon sigma bond. So I'll just write here lose carbon-carbon pi. And so that's favorable, of course. It's not always so obvious. So in general, what we're going to find with these electrocyclic reactions, in theory, is electrocyclic reactions can occur with any ring size. 3, 4, 5, 6, 7, 8-membered rings. We'll see variants of those. But when you look in synthesis, only 3 to 8 are the common ring sizes. Those are the ones that you'll see commonly. So 3 to 8-membered ring electrocyclic reactions are most common. All electrocyclic reactions, like all paracyclic reactions, are reversible. Not just hypothetically reversible, but you'll often find that they're opening and closing under the conditions of the reaction. And so that's why it's an issue that we need to address, what's favored, closing or opening. Okay, so 5 and 6-membered rings generally favor closure. Like this example that I showed you above here, but I'll show you some exceptions. That's not always true. In other words, what could you do to tip the balance away from the cyclic form? It's not hard to imagine things that you could do to make the product less stable after the cyclization. So let's take some examples where we lose that favorability. So I think you can see what's going on here. In this case, one of my pi bonds is a carbonyl group. And so if I push the arrows here, you can see that I'm losing a CO pi bond. And a CO pi bond is not a good bond for you to lose. That's not a weak pi bond like a carbon-carbon pi bond. And so in this particular case, you get an equilibrium mixture. You heat it up, you make the reaction go, and you get about a 2 to 1 or 1 to 2 ratio. So you're never going to get a high yield. There's nothing you can do. Well, I don't want to say there's nothing you can do, but at least as long as you're just using heat, you're going to get that awful ratio. You won't get a high yield of either open or closed. Here's a system where it's a little bit more complex to draw. I'm just going to draw 3 rings, but I want to focus on this middle ring here. And we can think about this process of opening. And if we really want to favor the ring-opened form, remember, generally 6-membered rings we expect the closure to be favored. But in this particular case, we can think up something obvious to do in order to favor this ring-opened form. And that's simply to make those pi bonds that you get part of a benzene ring. So in other words, if I make these part of a benzene ring, then you really want to have that product side of the equilibrium. So that means you have to have double bonds here and here, and here and here. And in this particular case, there's methyl groups that are sticking on there. Okay, so in this case, the ring opening, not ring closure, would be favored, even though it's a 6-membered ring. So here's an example. You can see there's a driving force here for this ring to open. 4-membered rings have about 26 kcals per mole of ring strain. I don't remember exactly what the number is for a cyclobutene with a double bond in there, but there's a substantial amount of ring strains. I'm not even going to draw the backwards, the reverse arrow there. So you can tell that ring wants to open up to relieve the strain in the 4-membered ring. Okay, so for 5 and 6-membered rings, generally closure is favored. But again, you have to worry about bond strength. Are you trading off? Are you removing strong pi bonds instead of weak carbon-carbon pi bonds? Is there some change in aromaticity that will drive the equilibrium? Or are you relieving ring strain? Those are kind of simple enthalpic issues for you to consider. Okay, so let's talk about strained rings. And I want to talk about light. So light can drive unfavorable reactions. It can drive unfavorable reactions. So let me make a point about light-driven paracyclic reactions. So the most important part is that the selection rules are reversed for paracyclic reactions. In other words, if you memorize some rule about what's favorable, anterofacial versus suprafacial, those rules get reversed when we pump in a photon. Or rules about 4n plus 2 being possible versus 4n, those rules are reversed. Suddenly 4n plus 2 is no good under light conditions, and 4n electrons are better. Let me give you an example where you can see the effect of this reversal of the paracyclic selection rules. So here's an example of hexafluorobenzene. And the important part is that there's double bonds, and we can think of the pi system as reacting as a 2-pi component. And so you can do a 2 plus 2 suprafacially, face to face. Right? If you just heat these things up, that will never occur. The orbital symmetry does not allow you to do a paracyclic 2 plus 2 between simple alkenes or between a benzene ring and a double bond. But if you irradiate this system, now it works. And now it can do a 2 plus 2. Face to face, suprafacial, suprafacial. And what's more is it just looks insanely uphill. Sorry, I've got so many halogens on here. The halogens are not the important part. The important part is that I just built a strained 4-membered ring, and I lost aromaticity in my benzene ring. 36 kcals per mole of aromatic resonance energy is gone now. And I just added 26 kcals per mole of ring strain with that four-membered ring. How can that possibly be a favorable reaction? It's a very simple idea. If I look at a photon, like an ultraviolet photon, depends on the wavelength, but they have more than 70 kcals per mole. Each mole of photons brings in more than 70 kilocalories per mole. So all this stuff about 36 kcals per mole or 20, don't worry about that. Once you bring in 70 kcals per mole of energy here, it can do stuff. Everything else kind of seems downhill with respect to bonds you form or bonds you break. I'm not going to draw the whole structure of cholesterol. There's an OH group here, there's an R group here, other methyl groups. So cholesterol looks something like that. It's a terpene natural product. You need it, your membranes need it. You have enzymes that can put an extra double bond right there. Your enzymes are doing that as we speak. They put an extra double bond. And so now if you look, this is set up for an electrocyclic ring opening reaction. So when you walk out into the sunshine today here in Southern California, what you'll find is that this will undergo an electrocyclic ring opening reaction in your body. So your body's doing electrocyclic ring openings. And I'm not going to draw the rest of the stuff there, but you get the idea. So light can drive this reaction. Let me go ahead and put the arrows there so we can see what's happening. You could draw them the reverse way. It's the same idea. Won't make any difference for your conclusions. There's another paracyclic process that follows on this. And we're not talking about sigmatropic reactions, but there's a 1,7 sigmatropic shift that occurs after this when you go out in the sunshine. It's going to be kind of hard to see, but you can see the 6 atoms in this tryene ring. Now there's 2 more atoms. So there's an 8-membered ring transition state here in which this proton can leap across and land on this pi bond. And that's a paracyclic process. It's called a 1,7 sigmatropic rearrangement. And we're going to talk about sigmatropic rearrangements in the next lecture, or sigmatropic reactions. But this is also a light-driven process. And your body does this. There's a couple of more enzymatic transformations that generate vitamin D, which you need for proper bone growth. But since your bones aren't your adults, your bones aren't growing anymore, so you might as well just stay inside and work mechanisms problems because you don't need sunshine anymore. If you're a little kid, you need vitamin D. Go out and play. Okay, so what's going on here? Seems kind of interesting. It's like when you pump in light, notice the 4-membered ring didn't close. What's up with that? What's up with over here with this type of, this is subject to a ring opening actually. Let me make sure I get this right. Or maybe not show that. But what's important is that this doesn't further undergo, I don't want to draw the arrows because it doesn't happen. This doesn't undergo an electrocyclic ring closure. There's something going on here. How do you know when you're going to get electrocyclic ring opening or ring closure? There must be some set of rules that tells you what light is going to do or what heating substrates is going to do. And in order to understand whether we're going to get cyclo addition or ring opening or 1,7 sigmatropic shifts, we're going to have to look at the molecular orbitals. Because the molecular orbitals will tell us which of those processes is possible or is completely impossible. And there's a stereochemical issue that's going on here. So I'm going to start off with the simplest system, well maybe almost the simplest system. Maybe a 3-membered ring is the simplest system. We're going to look at a 4-membered ring to try to understand what's called selection rules. How do you decide whether reactions are good or bad? So let me go ahead and draw this very simple ring opening of a cyclobutene ring, an electrocyclic reaction. So if I draw this arrow pushing, it'll look something like this, and then like that. And then we draw the ring opened product, butadiene. It's not really an issue what's the favorable equilibrium or direction. I want to think about what those arrows mean. What are those arrows telling us? Those arrows are telling us, really, maybe a better way for me to draw these arrows. I'm going to draw in red a better way to think about this. What must be happening, if I'm breaking this pi bond, this sigma bond must be donating into pi star. Right? If I'm somehow using this pair of electrons to break that pi bond, that means this sigma bond is donating into pi star. And if I'm using this pi bond to break this sigma bond, then the pi electrons must be donating into sigma star. That's the correct orbital analysis. So we better look at the symmetry of those orbitals in order to understand these two simultaneous processes. Both are occurring at the same time. And so let's draw those orbitals. Let's draw sigma, sigma star, and pi star. So let me start off by, I'm going to try to draw this edge on to give it this three-dimensional look. And I'm going to start off by drawing the pi-like orbitals when I draw this edge on. I hope that looks kind of edge on, like we're sitting in the plane. And so if I try to imagine what that pi bond looks like, let me use a different color because it'll look more exciting that way. We know what a pi-like orbital looks like. Looks something like that. That's kind of what the pi bond looks like. Okay, I didn't do a very symmetrical job, but whatever, you get the idea. And if I draw a pi star, right, there's a node in the middle. It's like an antibonding orbital. It's the opposite of a pi bond. And I just want to make the phasing the same as my picture in case it matters here. And there you go. You get this node in the middle. Now this opposite phasing top and bottom. So that's a picture of that pi bond. That's the pi orbitals. And let me just put a dashed line here. That's the energy of just a plain simple carbon p orbital. And so relative to the energy of a carbon p orbital, pi and pi star are, I'll just arbitrarily draw them here. One is below the energy of a p orbital. The empty pi star is above the energy of a p orbital. And so here's my orbitals. Pi and pi star, the empty one. Okay, so when I'm donating sigma into pi star, these are the orbitals involved. Let me draw those sigma bonding orbitals. Of course, sigma and sigma star sigma is lower in energy and sigma star is way higher in energy than a pi bond. And you already know that. You should know that just from the canonical energies of frontier orbitals. So now if I try to sketch the energy of that sigma-like orbital, sketch the kind of shape there, it'll give us a picture that we can keep in mind. Okay, so if I were to, this sigma bond that's breaking, this bond in front, when I draw this arrow starting from this sigma bond in front, I'm really representing, if I want to represent that with a molecular orbital, I want to draw something that looks like a sigma bond. Here's what a sigma bonding orbital looks like. There's electron density in the middle. That's where that pair of electrons spends its time. And if I draw sigma star, it's going to look like this. There's going to be a node in the middle, like you've broken the bond. And let me phase this. Okay, so that's sigma and sigma star. So when I draw these arrows, what I'm really drawing is I'm drawing the interaction of these electrons here in pi donating into pi sigma star somehow and breaking that bond. And simultaneously, the electrons in this sigma bond are donating into this empty orbital and breaking the pi bond. That's what this arrow pushing that I had here meant. That's what that arrow pushing meant when I drew the arrows in black there. Okay, it's hard to see how you're going to get any overlap. In fact, if it was really planar like I drew it there, the reaction wouldn't work at all. So we need to draw this substrate in a conformation that's realistic for this kind of orbital overlap to be effective. And you have to distort from a completely planar geometry. So it's not just that distortion is required, but a very picky and particular distortion is required. It's a very special distortion from planarity. So I'm going to try to draw 4 pictures here, or maybe 3. So here I'm going to try to draw a picture of this cyclobutene. And I'm going to try to draw this carbon. I don't know how to, I'm trying to bend it. I'm trying to take the bottom carbon and move it down and the top carbon and move it up. And I'm afraid I'm not doing the best job here, but there we go. So there's this pi bond in back here. I'll draw the pi bond, but really I want to draw the orbital for the pi bond. So there's a distortion that's occurring. And to help me see that, let me go ahead and try to think about what's required in order for this sigma bond to donate into that pi star orbital. Let me draw the pi star orbital again. So I can see both the sigma and the pi star in the same drawing. Okay, so there's my pi star. Now let me draw that sigma orbital. That's the orbital that has electrons in it. That's the empty orbital. And let me put some phasing on here. Right, by distorting this out of planarity, by distorting this sigma orbital out of planarity, I can start to bring this unhashed region up so it can overlap with this unhashed region. And if I don't distort, there's no way to get effective overlap. And at the same time that I'm distorting like that, this hashed area here is going to overlap with this hashed area. That's the distortion that's required in order to make this paracyclic process work. And the way to really see what's happening here is to draw these electrons, or sorry, these bonds, and pay attention to how they rotate. Because there's a particular rotation that occurs when I distort that in that way. What happens, in order to distort it in this way, I have to take this carbon atom and all its groups and rotate that counterclockwise. And at the same time, I have to take this group and rotate that counterclockwise. And we have a word for that. When they're rotating in the same direction, counterclockwise and counterclockwise, or clockwise and clockwise. We call that conrotatory. That type of distortion is referred to as conrotatory, rotatory. And that's the word we have to remember, conrotatory distortion. There's a particular implication of that. It's going to spin this group down here onto the inside of the diene, and it's going to spin this group over here onto the inside of the diene. And the converse is true for these outside groups here. This will spin to the outside of the alkene. Now they're all H's, so that's not interesting. We'll see some examples where it does matter. Okay, let me contrast this idea of conrotatory with what happens if one's rotating in and the other's rotating out. Let's take a look at that and the orbital implications for that. Before I do that, sorry, I don't want to draw that line in between. What I want to do is I want to look at the opposite. I forgot to draw the opposite orbital analysis. Actually, forget that. I'm not going to draw the opposite. You don't need to see the... What I was going to do is I was going to say, oh, but what about pi and sigma star? You reach the same conclusion, that you have to distort it in this clockwise plus clockwise way. Or sorry, counterclockwise plus counterclockwise, or clockwise plus clockwise. Okay, now let's see what happens if we don't distort it in that way. Because there's a way that you can distort it that doesn't help you and which doesn't lead to net bonding. So now what I'm going to do, let me use the red pen for this. I'm going to draw pi, and I could do the same analysis. Maybe I should try to switch this. I don't have this in my notes, but I'll try to switch this so it matches. Let's take a look at the same analysis where we're looking at pi star. And now what we're going to think about is what happens if we try to distort opposite directions. So one group, I'm going to start to distort inward. And if I'm drawing the sigma orbital, I need to phase these correctly. So there's the hashed region. So if I distort this so it's going clockwise, and then I have this other group over here, and I do it counterclockwise. So now they're going in the opposite direction. Counterclockwise. You end up with this very uncomfortable situation where now, maybe I should make these bigger. As I distort this counterclockwise, this now will overlap with the unhashed region. There's no possible way that this phasing can work out. If I distort both of these downward like this, this part of the bonding, the sigma bonding orbital, will overlap effectively, but this part will not. So the only way that you can do a ring opening or a ring closure with a 4-electron system like this is that it has to be conrotatory, and it cannot be the opposite, which is what we call disrotatory. And that means counterclockwise plus clockwise. So if they're mismatched, yeah?
What FMLs are you using there? So it's the sigma star?
Yeah, this one over here is pi star, and this one is sigma.
Yeah, and then
So,
on the right.
and then over here, it's, well, I drew it's not a node because they're phased correctly.
Okay.
Because the phasing is the same. That's a sigma
Okay.
bond. Even though I was trying to make it look kind of like P-like orbitals, but they're phased the same. That's a bond in between there. Let me just draw that. That's still sigma. Okay, so we have to pay attention to this conrotatory, disrotatory bit. Let's take a look at what happens when you go beyond a 4-membered ring. So for the 4-membered ring, we would draw something like this. And for the 6-membered ring, what's different? And the transition states are this, it's the same transition state for opening and closing. It doesn't matter whether we're talking about opening or closing. It's the transition state that matters. Is the transition state any good? So let's go ahead and take a look at this conrotatory ring closure again. And I'm sorry, I'm going to draw this same weird distorted thing, so it's going to, hope you're getting better at drawing that distorted thing. This time I'm going to draw the pi orbital up here rather than pi star. Let's focus on this pi-like orbital here. And the pi, or if I think about the pi bond donating into this and breaking this sigma bond here, that means I need to draw the sigma star antibonding orbital here. And I need to get the phasing correctly. Okay, so now that's pi, and now this is sigma star. So when these electrons in this pi bond donate into sigma star, that works out. As long as I have this conrotatory distortion. As long as this rotates that way, and this rotates in the same direction. And so this is counterclockwise, and this is counterclockwise. And that works. Works beautifully. Doesn't matter whether I'm talking about sigma donating into pi star or pi donating into sigma star. I'll reach the same conclusions. But now let's look at the 6-electron example. Instead of drawing just a simple alkene back there, I'm going to draw a diene in the back. So over here I just have a simple double bond, but now I've got a diene. And let me draw the HOMO. Where's that most reactive pair of electrons? Or what does it look like for a diene? And it's not the same as it is for a simple 2-electron pi system. That's what the most reactive pair of electrons looks like for a diene. Now there's a node in between. Now on one end of my pi system, I've got the hashed part on the bottom, and on the other end of my pi system, I've got the hashed part on the top. So when I try to think about the interaction of this pi system, pi, with a pair of electrons in there, with the antibonding orbital, if I do this con-rotatory distortion, and this time I'm going to distort these things downward. So this would be counterclockwise. And this one I'm going to try to distort also counterclockwise. And let me draw that antibonding orbital now. Here's the antibonding orbital. And I'll draw the other end of the antibonding orbital. And the phasing is arbitrary. There is no way that you can phase this in order to get it to work out. So here, if I spin this side counterclockwise, I get effective overlap. If I spin this towards the top, this now overlaps effectively with this end of my pi system. But I get a total antibonding interaction on the other side. This doesn't work out. You can't have con-rotatory distortion for a 6-membered ring. And it's not the size of the ring that matters, it's the fact that this is a 6-electron system. So let me put this in black here. I'll just write, no, you can't do this in a con-rotatory fashion. Whereas here, you can and should do con-rotatory distortion for a 4-electron system. Now, I'm not going to draw out the 8-membered ring, but what you would find if you drew the 8-membered ring is when you draw a triene in back, you would reverse the rules. Now con-rotatory would be good. So for lack of time, I'm not going to draw the 8-membered ring, the 12-membered, or whatever the next one is, the 12-membered ring, etc. Okay. I guess what I mean is I'm not going to draw the orbitals for that. Let's get down to the, let me just make one simple statement. This is the last time you're ever going to see this. Just like me, you will have heard this in one class, and then you'll never look at it again. You'll never look at those orbitals again. What we're going to do instead is we're just going to draw it without the orbitals, and we're just going to try to envision that distortion without thinking about the orbitals. If you really want to analyze the stereochemical consequences here, and let me put R groups here that are trans to each other, right? You don't need to draw the orbitals to envision what con-rotatory means. You can just imagine those two sets of groups spinning. Usually when you analyze an electrocyclic ring opening or ring closure, you just pay attention to the end groups. You don't pay attention to the pi bond. That's the simple way to do this. Now there's two different con-rotatory ring openings and ring closings. One is where they both go clockwise, and the other is where they both go counterclockwise. And they're both equally, unless it's unsymmetrically substituted, but they're both possible. So when we draw the 6-membered ring, again, you don't need to draw all those orbitals. You just want to pay attention to these, and I apologize for my not good. It looks kind of like a flat ring. So you just pay attention to these end carbons at the ends of each pi system. So for a 6-membered ring, it's disrotatory that's favored. Right? If you want to form bonds simultaneously, you need to have these flip in opposite directions, either both flip inside or both flip outside. And then if we go to the 8-membered ring, it's going to be kind of hard to draw edge on, but we'll try to imagine what that would look like. Something like this. And again, you don't have to draw all the orbitals, sigma star and pi star. You just pay attention as rotation. So disrotatory, I never finished this up. So disrotatory, you just need one to go clockwise, the other to go counterclockwise. So disrotatory means that one R group, if this is going counterclockwise, then I need to make this other one go clockwise. And the implication of that is that one R group would spin outside and the other R group would spin inside. Let's draw the product of that disrotatory ring opening process. It would look like this. One R group would be outside, the other R group would be inside. And it helps to put the H atom on there as well so you can see what's going on. That's the implication of a disrotatory ring opening. It determines whether the double bonds are E or Z. Okay, for an 8-membered ring, it would also be conrotatory. Rotatory, like a 4-membered ring. And then if you drew out the ring-opened product, if these are conrotatory, so this would go, here I'm drawing it counterclockwise. So I also need to draw this one. If it's really conrotatory, this would also have to be counterclockwise. And so in one case, the R group would spin outside, H group would be in. The other case, the R group would spin outside, and the H group would spin inward. So again, this conrotatory, disrotatory stuff determines double bond geometry, E versus Z. Okay, so I'm not going to draw the next, so 4, 6, 8, 10. I'm not going to draw the 10-membered ring. That would be disrotatory. 12-membered ring would be conrotatory, etc. And again, it's not really the ring size, it's the number of electrons in the transition state. And we have a simple rule for that. If you count the number of electrons in the transition state, it's basically determined by how many curved arrows you're drawing. Each curved arrow involves 2 electrons. For the reactions that I've shown you, we haven't invoked light. Anything without light we call thermal, even if it occurs at room temperature. If you're not pumping photons in there, then it's a thermal reaction. And so for thermal reactions, our general rule is anything with 4 n electrons is going to be conrotatory. A 4-membered ring, an 8-membered ring, a 12-membered ring, those will all operate through this conrotatory distortion. 6-membered rings are opposite. Anything with 4n plus 2 electrons in the transition state, an electrocyclic reaction, will be disrotatory. So that would be 2 electrons, 6 electrons, 10 electrons. And we have a very simple rule to predict this. It turns out that all of those rules get reversed if we go to a photochemical reaction. And why is that? If you pump an electron into one of these pi systems, you're going to push an electron into the next higher energy orbital, which then has the opposite phasing. Pushing an electron into a higher energy orbital means we need to draw the next higher energy orbital because it's now occupied. And you reverse the phasing. So all of these rules will be reversed. So now, under photochemical conditions, you find that you reverse those rules. And we don't have to draw the orbitals out. We can just memorize this very simple set of rules. Now, you really only need to memorize one example. And you can back out all the rest of the rules. And there's all kinds of mnemonics for this. Here's one, 6 points for a touchdown. 6 electrons is thermal and it's disrotatory. If you know that, you can subtract 2 electrons and learn the rest. When the heat is on, 4 is con. I mean, there's an endless number of these gimmicks. You just need to memorize one case, and you can remember all the other examples. You can back out all the other examples of whether it's disrotatory or conrotatory. Okay, so let's try to apply this, because this seems very abstract now. Let's take a look at some electrocyclic reactions. And I'll test you to see if you understand this, if you can use these kinds of rules to predict whether things are conrotatory or disrotatory. I'm running out of pen power here. Switch black pens. This is a system that's very simple to make. There were triple bonds here, and they reduced it with Lindlar's catalyst. And this undergoes, room temperature undergoes an 8 electrons cyclization to make an 8-membered ring. Right here. Actually, let me just push the arrows for that. Okay, conrotatory or disrotatory? Four electron is conrotatory, 6 electrons, disrotatory, 8 electrons, conrotatory, 10 electrons, etc., and so forth. And again, you only need to remember one of these, and you can remember the rest. So this is going to be 8 electrons. It's going to be a conrotatory ring closure. So conrotatory means sometimes it will help, in fact, most of the time it will help you to draw all the substituents on your double bond, so you can see rotation. If you don't draw those hydrogens, it can be very hard to see what's happening here. So when you draw out the product, which is a triene, so if I flip this up like this hydroxy methyl group is going to go up. And if I also flip that in the same direction, now the H is going to go up. And so that would be the stereochemistry you would predict if both carbons are rotating in the same way. And I'm not sure how am I rotating this. I don't know how to. If I were rotating that up, it would be like this. There we go. Same direction, windshield wipers or something like that. And that would lead to this stereochemistry. Under the conditions of the reaction, this keeps going. I guess I shouldn't tell you. So this is going to be a 6-electron process when this 6-electron system now cyclizes. So this now cyclizes to make a 6-membered ring. And yeah, it also generates a strained ring, but it's okay. And I hope I get this right because I reversed the stereochemistry from what I originally drew here. Okay, so 6 electrons, disrotatory. 6 TD, or you could have remembered this one, but there's no light. I didn't draw any light here. This is a reaction just goes at 25 degrees Celsius. So again, calling it thermal doesn't mean we're heating it. It just means that we're not adding any light. And so this is a disrotatory ring closure. Disrotatory means things spin in the opposite direction. So opposite direction, not like this. That's conrotatory. Clockwise, clockwise. Counterclockwise, counterclockwise, that kind of thing. Disrotatory means opposite directions. And so in this particular case, you would get that. So in other words, if I spin this one up, I would now spin this one. If this one is spinning in a clockwise direction, if this carbon, then I would have to spin this in a counterclockwise direction to make that work. Or I guess I'm spinning the H counterclockwise here. And here I would have to spin this H in the opposite direction, which is clockwise. That's what disrotatory means. Okay, so, and you can isolate this in 55% yield after this 2-electron cascade. Okay, let's take an example of a 5-membered ring. So this is 8-membered rings, 6-membered rings, and really the important thing is 8 electrons and 6-electron processes. Let's take a look at a 5-membered ring. Here's a classical reaction that's used in synthesis. This is the way they make CP star rings for organometallic complexes. It's a 4-electron process. I think you can imagine that you could add a Grignard reagent to an ester and add twice. So if you took ethyl acetate and then added a Grignard reagent twice, you'd get this alcohol in one step. And then all you have to do is treat this with acid. Toluene sulfonic acid. And that protonates this OH and makes it into a leaving group. And so now I have just one big extended pi system. And how many electrons are in this pi system? There's 4 electrons. This is a 4-electron process. This is an intermediate. There's no light involved here. And that means it's going to close through a con-rotatory ring closure process. I'll go ahead and draw the arrow pushing. It's cationic when you start. It's going to be cationic when we finish. According to my arrow pushing, the positive charge is going to end up over here in the 5-membered ring. Right? The positive charge won't disappear. So the end, or at least the intermediate that you get, looks like this. And I'll draw the H's that were there before. Let me wait till we talk about stereochemistry. Okay, this is con-rotatory. So that means if I spin this group, if I spin the methyl group up, that means this inside group here has to also go up. If the methyl group goes up, this H has to go up. And so you'll get one of the 2 enantiomers that you get 2 equal enantiomers here. Looks like this. But of course, you still have counterions floating around from your toluene sulfonic acid or water. Doesn't matter. Something with lone pairs can now pull the proton off, and that's what gives you not CP star. You still have to deprotonate it to get CP star. Let me make sure I've got the... And then when you pull a proton off of the cyclopentadiene, you can use it as a ligand for organometallic complexes. So that's a very simple Nasaroff cyclization to make 5-membered rings. That's not the most common version of the Nasaroff cyclization. So we just have a slight bit of time here, and I'll show you the more classical version of the Nasaroff that's used in synthesis. It doesn't involve toluene sulfonic acid. Here would be a very classical Nasaroff cyclization. You start with a dienone, just some carbonyl with alkenes on each side, and you treat that with a Lewis acid. So in this case, they use a catalytic amount of aluminum trichloride. And so when that coordinates, it's kind of like creating a carbocation. I'm going to draw one resonance structure of that Lewis acid complex. And it would look like this. There's no methyl group down here. So coordinating a Lewis acid to a carbonyl is kind of like creating a carbocation at this position. And this can undergo room temperature, can undergo a Nasaroff cyclization. It's a 4-electron process. There's 4 electrons in this pi system. And you can see if I start with a cation here, somewhere in this, I'm going to end up with a cation somewhere. It's going to end up over at this position when I'm done pushing my arrows. You get a racemic mixture of this intermediate. Right? There's nothing about this. There's no chiral centers on my starting material to control the stereochemistry. And so I'll get a racemic mixture of these 2 cyclized products. Right? It can cyclize, there's 2 different ways to go con-rotatory. clockwise or counterclockwise. There's 2 ways. Yeah.
Is that happening on the other side?
What did I, let's see, this will go down, that'll go down, this will go up. If this goes down, this goes up.
I mean the alkene on the other side of it.
Oh, what did I do? I did something, yes, sorry. It's a resonance structure, but it's my arrow pushing says to make that up. Thank you for asking about that. And then you've got some sort of counterions floating around in your reaction mixture, and those can simply pull off the proton in order to give you your next intermediate. So the final product of these types of Nasaroff cyclizations are enones. If you walk through all the arrow pushing here. You know, the enolate, you don't isolate the enolate gets protonated. You couldn't have known this. What you couldn't have known, well, maybe you could have known this, that the proton, you protonate the enolate on the top face so that whenever you make 2 fused 5-membered rings, they always need to be cis. It would be a 9 kcals per mole uphill if you put these 2 groups on opposite faces. Okay, so you protonate the enolate afterwards, and that's what sticks the proton there. Okay, so we've run out of time. I've got one last thing to talk about when we come back, and that is electrocyclic reactions of 3-membered rings. But I think you're ready to go with the problem set. I'm sorry, we forgot to hand out the problem set on Wednesday during discussion, but it's posted online, and I think Gene brought those with him today. Okay, I'll see you guys after President's Day.